Okay, students, this lesson is called Precipitation and Predicting Products. In it, we're going to take a look at solution chemistry. How do we figure out what substances will remain dissolved in solution when a couple of things are mixed and which things will not? First of all, a quick definition. When we say precipitation, we mean something falling. So kind of like leaves or rain or snow precipitating. That means they're falling, coming down from the sky. And what we find with the mixing of solutions is that sometimes a solid substance falls out of solution. So chemists appropriately say that that substance is a precipitate, or it precipitates out of solution. An example would be when we mix barium nitrate and potassium chromate. Here's a picture of the two solutions. The yellowish potassium chromate is in the grad cylinder, and the colorless barium nitrate is in the beaker. And as you add the yellowish substance to the colorless solution in the beaker, it completely, it forms a yellow cloud. Let's say you let that solution settle to the bottom of the beaker. The precipitate will then fall down, and the yellowish barium chromate is the precipitate that goes to the bottom of the beaker. Let's say we were asked to diagram this. Basically, what we're asking is, when you mix a couple of things together, how do you figure out what's going to settle to the bottom and which ions are still floating around? Look at the key on the right side. We've got the red spheres that are potassium ions. The purple spheres are barium. The cluster of 1 blue and 3 reds, that's nitrate ion. And the cluster that's 1 yellow and 4 red, that's chromate. In the beaker, before a precipitation reaction has occurred, as pictured on the left, all of the ions are in solution. They're interacting with the water molecules, which are not being pictured here. And then after all of the molecules have had a chance to interact, usually by stirring or swirling or just giving the molecules time to interact with each other, the barium finds the chromate, and when that happens, it forms a solid that falls to the bottom of the beaker. Now, here's how we represent that equation. This is going to be an important part of this lesson. The way that we represent this looks like this. So K2CrO4, that's potassium chromate. That was one of the reactants. BaNO3, that's barium nitrate, another one of the reactants. Notice that there's this AQ in parentheses after this formula, kind of down low as a subscript. That stands for aqueous. And aqueous is a state of matter that means dissolved in water. When we study solutions, we're always going to be considering, at least in this class, solutions that are solid particles dissolved in water as the solvent. So aqueous solutions, AQ means they are interacting with the water. Now, in the equation, we see an arrow and then BaCrO4 with an S after it. That S stands for solid. It means it's not aqueous. That's something that is no longer dissolved, and if it's a solid, it's eventually going to settle to the bottom of the beaker, meaning it's more dense than the liquid. And we have 2 formula units of potassium nitrate with an AQ, meaning the potassium ions and the nitrate ions remain dissolved. We're going to develop a schema for understanding all of this as we go through this lesson. But for now, I want you to notice that AQ stands for aqueous. That means the substances are still dissolved. S stands for solid. That means the substance that fell out of solution. The term we give that is the precipitate. Okay, that brings us to a couple of terms. Solubility is the ability of a substance to dissolve. That kind of makes sense. The ability to dissolve is its solubility. Just put those words together. If something is described as soluble, that means that it is able to dissolve, and we give it the aqueous designation. You might see the AQ after its formula. So that means A, it's floating around in solution, still interacting with water, even after the reaction has happened. And when we write the chemical equation, we put AQ in parentheses after its formula. Insoluble means not. So there's a prefix in, meaning the opposite, and is not able to dissolve. This is referring to the solid precipitate. This is the substance that would be sitting at the bottom of the reaction vessel, like barium chromate in our previous example, after the reaction has occurred. And if we're writing the equation out, we would put a little S in parentheses after the substance's formula, meaning it's a solid. It's not going to be floating around. Now here's the problem with these terms. The letter S almost seems like it should represent soluble, but it means the exact opposite. Soluble means dissolved. Insoluble, which is designated with an S, means not dissolved. So I understand how those would get confused, and I totally understand why many students do get those confused, but please, please, please try to get those straight. Soluble means not dissolved. I'm sorry, soluble means, there you go, I did it myself. Soluble means it is dissolved. Insoluble means it's not dissolved, and you put an S after it. Okay, when we encounter problems, I'm going to present to you, and this is going to be unique for us, I'm going to just give you two reactants. I'm not giving you the products. So this is totally new. I'm simply going to give you two reactant formulas. When you get that, the first step is to identify what ions you see. Use your knowledge of chemical compounds. So that means get your periodic table out. Look for the metal ion. It's always going to have, when we encounter solubility equations, it's only going to be ionic compounds, which means every compound is going to have a metal in it. So look for the metal. Okay, first and foremost, look for that metal. Write down the ions that make up the reactants. Identify the positive ones and the negative ones. As you do that, watch for polyatomic ions. So there was that list from way back in first semester of the polyatomic ions. That's still relevant. You still get to use that list, but you still need to know how to use it. Okay, next, note which ions are positive and which ions are negative. And the way to distinguish them is, chemists throughout the world are always going to list the positive ions first. So positive ions come first, negative ions come second. Always, 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 always. And please remember, as we encounter chemical formulas for ionic compounds, it's always going to be a positive ion attracting a negative ion. If you start attempting to put together two positive ions together, number one, it'll look funny to a chemist who knows what he or she is doing. But remember that the positive ions would repel each other. And if you attempt to put two negative ions together, a chemist is going to know that that looks funny because the two negative ions are going to repel each other. It's positive with negative always, and the positive ions listed first. Okay, write proper formulas for the products. You're not given the products ahead of time. So what we're going to ask you to do is write a new or novel combination of ions. The new way that you can pair positive with negative, that's really important. I want you to pair those two together. Remember, positive will still pair with negative, and the positive ion goes first. Third step, once you've written the product formulas, write the full balanced equation. You might need to add coefficients. So the number of atoms on both sides of the equation needs to be equal. So every single atom type needs to match on the left side and on the right side. And then lastly, and here's the new part, I think you could have done steps 1 through 3 up until this very last point. Until now, I'm going to ask you to write AQ for substances that are dissolved and S for the substances that are not dissolved. Sometimes you do not get a precipitate. That's why I say write S after the precipitate if you get one, but you might not get one. It's possible to mix two solutions together and have no precipitation. Let's go through an example. And I think as we go through an example, we'll kind of get a hang of this. So let's say I'm giving you a situation where we're mixing AgNO3 and KCl, silver nitrate and potassium chloride. The first thing we're going to want you to do is identify the positive and negative ions. Remember, the positive ion always goes first. So I'm writing Ag, and I'm color coding it red in this slide. The red Ag means that's the positive ion. And on your periodic table, you would see a silver Ag. And that is one of the, even though it's in the transition metal block, it's always a +1 charge for silver. Potassium, that's the other positive ion. It's in column 1, and so it has a +1 charge. The negative ions, NO3, that's one of your polyatomic ions. If you don't have those memorized, that's fine. Just have the list of polyatomic ions out. And you would see that NO3 is a 1- charge, and it's nitrate. Cl, that's chloride ion, group 17 on the periodic table. That's in the column that has a 1- charge. So let's list those ions. The positive ones are Ag with a 1+, K with a 1+. The negative ones are NO3 with a 1-, and Cl- with a 1- charge. Here's a picture. The pictures are optional. As far as I'm concerned, you're welcome to draw the pictures if that helps. You're not required to draw them. But here are the ions as pictured before reacting. You see the silver spheres are the silver ions. The cluster of 1 blue with 3 reds, that's nitrate. They're all floating around in solution. In the other reaction vessel before mixing, you have potassium represented with the tannish spheres and chloride ions represented with the green spheres. Okay. The products of the reaction will be the new ways that you can combine a positive ion with a negative ion. Initially, Ag was paired with NO3, and K+ was paired with Cl-. What are the new ways that we can pair positive with negative, listing the positive ones first? Well, if Ag was initially paired with NO3, let's pair it with Cl. So Ag with Cl, and then the other new combination would be the K+ ion with NO3-. Thus, we make the formulas AgCl. Notice it's a 1+ with a 1- in the charges of the ions. So AgCl, you don't need any subscripts to make that formula balance. And K with NO3, K+ and NO3-. Remember, an ionic compound is neutral overall. So if we needed to, we would add subscripts to indicate additional atoms to make the charges balance, so that the positive charge represents or equals the negative charge. And always remember to write the positive ions first. So putting all that together, our initial substance were AgNO3 and KCl, and then the products that we figured out via new combinations of ions were AgCl and KNO3. Now the new part. Oh, by the way, this equation as written is balanced because there's 1 silver on the left side and 1 silver on the right. There's 1 nitrogen on the left. There's 1 nitrogen on the right. There's 3 oxygens on the left, 3 oxygens on the right. There's 1 potassium on the left, 1 potassium on the right, and 1 chlorine on the left and 1 chlorine on the right. So we are a balanced equation. No coefficients need to be written. Now here's the new part. Considering states of matter. When you mix silver nitrate and potassium chloride, you get a cloudy white mixture, or a cloudy white substance appearing in that mixture. And it turns out that that cloudy white substance is silver chloride. We put an S after it, meaning it is the precipitate that does not dissolve. It will eventually, if you give it some time, to fall to the bottom of the reaction vessel. The other substance that's new, the product, KNO3, is dissolved, AQ. Here's a way to picture it. Here are our 2 solutions before reacting. Here are the ions after reacting. Notice that at the bottom of the picture, we see the silver spheres and the green spheres, the silver and the chloride. So AgCl is the solid that had precipitated. Remaining in solution, we have potassium ions and nitrate ions. They stay there. So if one of the product compounds does not dissolve, it falls or precipitates out of solution. That will often, but not always be the case. Let's consider some equations where I'm going to ask you to work these out. First, I'm going to ask you to write the balanced equation for these reactions that occur when the 2 reactants as written here are mixed. Also, I'm going to give you extra little hints here. Positive ions are going to be colored red, and they're going to be listed first. Positive ions, and then negative ions are listed second. I'm going to give positive ions red, negative ions blue. So the first example, we have AgNO3 and LiBr. Okay, first, let's think about, excuse me one second, I'm going to get my notation here. Okay, and I'm going to give you a hint that NO3 minus is nitrate ion. Just trying to get one thing here. One sec. Anyway, all right, here we go. Now we've got it. Okay, so we've got the polyatomic ions listed. NO3 minus is nitrate for the first one. So if we've got Ag, which is silver is in the transition metal block, and it is a +1 charge. NO3 minus is one of our polyatomic ions. It's NO3 with a 1 minus charge. Lithium is a column 1 ion, and it is +1 charge. And Br is a group 17 element, and it is a 1 minus charge. So luckily, go back. Okay, so when we turn on the fan, there we go. Okay, so if we are asked to write formulas, we're looking for the new ways to pair positive ions with negative ions. So if initially silver was paired with nitrate, the new way to pair a positive with a negative ion would be lithium with nitrate. And since I know that lithium's a 1 plus and nitrate's a 1 minus, it takes one ion of each in order to make a neutral compound. So LiNO3. Notice that that 3 is part of the nitrate ion. It doesn't mean there's 3 nitrate ions. There's only one of them because the 3 is part of a single nitrate. The other new product is silver paired with, well, if it was initially paired with nitrate, it's going to, in the new combination of ions, be paired with bromine. Silver is itself an element in the transition metal block that is a 1 plus charge always, and bromine is a 1 minus charge. So it just takes one ion of each to make a neutral compound. So we've got LiNO3 and AgBr. Notice that it's always positive ion paired with negative, and the positive ions listed first. In the next equation, we've got Na. Na is sodium ion, group 1, so a +1 charge. It's paired initially with hydroxide, which they tell you below is OH with a 1 minus charge. It's polyatomic. That's mixed with calcium, which is a group 2 element, so +2 charge, and it's paired with iodide ion, which is a 1 minus charge. So let's think of the new ways that we can pair a positive with negative. Well, what if we took sodium and paired it with iodide? A +1 sodium paired with a -1 iodide. That's a good formula. Na, positive ion listed first, I. negative ion listed second. And then the other combination is, what if we take calcium and pair it with hydroxide ion? So I'd write Ca, because the positive ion goes first. And then because Ca is a 2 plus charge and hydroxide is a 1 minus, it takes two hydroxides to cancel out the size of the charge on the one calcium. So Ca, open parentheses, OH, and then a 2 makes for a neutral compound. Next, consider the balancing of the equation. The first equation was fine. We didn't need any coefficients there. But here, because we have this subscript 2 outside the parentheses for hydroxide, it means that in order to balance the equation, we need to put a big coefficient, not a subscript, but a big coefficient out front in front of NaOH. We would also need to put a big coefficient out front, therefore, in front of NaI, which matches the I2, which is in the CaI2, the other reactant. So by putting those coefficients 2, we've got 2 sodiums on the left side and the right side of the equation. We have 2 iodide ions on the left side and the right side of the equation. So that's a good balanced equation. Next one, number 3, CuSO4. Now they give you down below the formula for sulfate ion. It's one of your polyatomics and it has a 2 minus charge. If one sulfate ion was needed to cancel out the charge on one copper and sulfate was a 2 minus, then copper's charge must have been a 2 plus. So sometimes it's helpful just to list the ions. In this case, it's going to be helpful. So I'm going to list positive ions. All right, POS for positive. Cu2 plus. The other positive one is going to be PB. And then I want you to think carefully about this. PB in a neutral compound is paired with 2 nitrates, and each nitrate is a 1 minus charge. So 2 polyatomic nitrate ions, which are 1 minus each, means that in order to make that compound neutral, PB must have been 2 plus. So our positive ions are Cu2 plus and Pb2 plus. Our negative ions, well, actually they listed these for you in the parentheses here, is sulfate SO4 2 minus and nitrate, which is NO3 minus. So what are the new ways that we can pair ions, positive and negative, together? Well, we can pair copper with nitrate. And since the copper is going to be a 2 plus, the nitrate, it requires 2 of them to cancel it out, make a neutral compound. So one of our products is Cu parentheses NO3 close parentheses 2. The other one is going to be Pb paired with SO4. Now think about that one. If a Pb ion, which was 2 plus, pairs with a nitrate ion that is 2 minus, they have the same magnitude of charge. So 1 ion of each makes the neutral compound. So it's going to be Pb and SO4. Please note the 4 doesn't mean there's 4 sulfate ions. The 4 is part of a single sulfate ion. Okay, and let's see, are we balanced? There's 1 copper on either side of the equation, 1 lead ion, there's 1 sulfate ion, and there's 2 nitrate ions. So yes, we are balanced. This is a good way to do it. Let me figure out how to get the pen to go away. Here we go. How do we know which stub, when we're considering precipitation? It's a natural question to ask. Okay, so you can write formulas for the products, but how do you know of the products which ones are going to stay dissolved and which ones are going to precipitate? And interestingly, and we'll see this in the example shortly, if you've got a reactant, in order to make it react with another solution, it has to be dissolved itself. Otherwise, there's no mixing. So automatically, the reactants are going to be aqueous. So if you wanted to figure out for the products which ones are going to stay dissolved and which ones will precipitate out, one strategy is mix several hundred, maybe even several thousand solutions together and write down some trends. We're going to do something like that in a lab called Mission Insoluble later in this unit. But let's say that you don't have access to hundreds or even thousands of solutions. The shortcut way to do it is to trust a list of solubility trends that have been developed over centuries of experimentation by other scientists. And these trends, number one, you won't have to memorize, but you will have to be able to use this list effectively as we encounter problems. First, let me show you what the list is. Rule number one, any salt or when we say salt, we mean ionic compound. So any ionic compound or salt that contains the ion nitrate is soluble automatically. Rule two, salts that contain metals from group one. So on your periodic table, look at lithium, sodium, and so on, everything in that first column, or ammonium ion, those are soluble. Rule three, here there are some exceptions. There's a general rule and then there are exceptions to it. Salts that contain chloride ion, bromide ion, or iodide ion are generally soluble, except when they're combined with silver ion. So like silver chloride, that was one of our examples earlier. That was a solid precipitate. Or lead ion, lead 2 specifically. Or you won't often see this, but the Hg2 with 2+ charge, that's actually a polyatomic ion. It's called the mercury 1 ion. If any of those three, chloride, bromide, or iodide paired with that, it would not be soluble either. Rule 4, generally speaking, ionic compounds that contain sulfate ion are soluble, except for barium sulfate, lead sulfate, mercury 1 sulfate, or calcium sulfate. Those 4 salts are not soluble. Then I'm going to give you 2 rules that are telling you what's not dissolvable or not soluble. So the first 4, soluble, the next 2, not soluble. Salts that contain hydroxide ion, not soluble. Salts that contain, and then there are 4 ions here to be aware of, sulfite ion, which is S2-, carbonate ion, CO3 2-, chromate ion, like barium chromate from the very first example, CrO4 2-, or phosphate ion, PO4 3-, are not soluble. Please keep in mind, these rules apply only to the ionic compounds. You should assume that unless told otherwise, all covalent compounds are soluble. Okay, with this list in mind, let's return to the 3 balanced equations that we had written already. So here's our last challenge together. We're going to write AQ or S in the little parentheses after the formula for each of the substances. And we're going to try to follow the rules of the solubility rules gave us. So let's take a look at the first one. First, I see NO3. And whenever I'm thinking of NO3, I'm thinking rule 1. So what I'm going to do notationally here, students, is I'm going to write the rule number that would apply. Sometimes more than one rule will apply. Okay, but in this case, NO3, that's the only rule, rule number 1. And at the very top of our list, any salt that contains nitrate ion is aqueous or is soluble. So I'm going to put that AQ designation right after AgNO3. Next one, LiBr. Well, I know that lithium is a group 1 metal, meaning it's an ion found in the first column of the periodic table. So rule 2 is going to apply. But also, I see bromide ion present. So I'm thinking rule 3 also is going to apply. Sometimes you can have more than one rule apply. So if you look at rule 2 of the solubility rules, group 1 metal salts would say that this salt should be soluble. Also, rule 3 says that, generally speaking, ions that contain chloride or bromide or iodide are soluble as well. There are some exceptions, but this is not one of the exceptions. So rules 2 and 3 reinforce each other to make this substance aqueous. So I'm going to give it an AQ designation. AQ. Next one, let's look at LiNO3. I'm just reading left to right here. I do see nitrate ion, so I'm thinking rule 1. But I also see lithium, which is a group 1 metal. Both rules 1 and 2 apply, and they reinforce each other, making this salt aqueous, or designating it as soluble. So we'll give it an AQ. AgBr. Take a look at rule 3 and read it all the way to the end. Generally speaking, groups as ionic compounds that contain chloride ion, bromide ion, or iodide ion are soluble, except, and then read that first exception, when combined with silver. So that means, according to rule 3, this substance is not aqueous. It's insoluble. And so I'm going to give it an S designation, meaning it's the solid precipitate. Down to equation 2. NaOH. Here is a really interesting one, students. Rule 2 applies. Sodium is a group 1 metal. But also, rule 5 applies because this ionic compound contains hydroxide. By virtue of rule 2, I would designate this salt to be aqueous because it contains a group 1 metal. But by rule 5, I would designate this salt as not soluble. I'd give it the S designation because it contains hydroxide. Which rule should we follow? Here's where it gets interesting. Please remember this. The solubility rules are written in order of importance. In other words, rule 1 is the most important rule, and if it conflicts with any rule further down the list, you should ignore that rule that's further down the list. The next most important rule is rule 2. And that says that salts that contain group 1 metals are soluble, and you should disregard any rule further down the list. So in this case, rule 2 applies, and rule 5 would apply, but since rule 2 is listed higher, rule 5 is not, it's like rule 2 trumps rule 5. So rule 2 says that salt is soluble. Give it the AQ. Take a look at rule 3 for CaI2. That says that groups that ionic compounds that contain chloride, bromide, or iodide, and here's iodide, are soluble except for, and then they give you some exceptions. Ca is not one of the exceptions. So give this salt the AQ designation, meaning it is soluble. Next one, I'm reading left to right here. CaOH3. The only rule, OH2, sorry. The only rule that would apply is rule 5. According to rule 5, salts that contain hydroxide ion are not soluble. So that means this gets the S designation, meaning not going to dissolve. NaI, look at rules 2 and 3, which reinforce each other. They would both designate this ionic compound or salt as aqueous. Last equation, CuSO4. Take a look at rule 4. It says that sulfate salts are soluble, with some exceptions. This is not one of the exceptions, so give it an AQ. PbNO32, look at rule 1. That one, by the way, nitrate salts are like, there's no designation, and it's the very first rule in the list. So if you ever see nitrate salts are amazing. Nitrate salts always dissolve. And here, lead nitrate, that will dissolve. Give it the AQ. Similarly, CuNO32, well, rule 1 applies, and there's no exceptions for it. So AQ, whenever you see nitrate. Now, for PbSO4, here's an interesting one. Read rule 4 carefully. It says, generally speaking, sulfate salts are soluble, but read all the way to the end, except when combined with barium sulfate, lead 2 sulfate, here's lead 2 sulfate, mercury 1 sulfate, or calcium sulfate. So because the exception would apply, this gets the S designation. Woofta, that's quite a lot, students, right? There's a lot of work to go on here. I just want to point out one thing. If we take a look at the substances on the left side of the reaction arrow for all three equations, notice that everything that we wrote down was aqueous. And I'm going to give you a time-saving hint here. This will save you time in the homework. Any reactant is going to be aqueous. So any substance on the left side of the arrow is going to be aqueous, because in order to get that substance to react with another substance, it had to be dissolved in the first place. If it weren't, it wouldn't react. So save yourself some time. Whenever you see a reactant, put the AQ. For the products, when I say products, I mean substances on the right side of the reaction arrow. For these substances, I need you to consider all of the solubility rules. So think carefully. All right, does rule 1 apply? Start at the top of the list. Does rule 1 apply? Yes, no. Does rule 2 apply? Yes, no. Does rule 3 apply? Yes, no. And keep working your way down. I would suggest listing all of the rules that do apply. You could just go work down the list, and when you see the first one that does apply, go for it. But I just think it's helpful to list the ones. If there's more than one that applies, go ahead and list it. Ask yourself, do those two rules reinforce each other, or do they conflict? If they reinforce each other, there's no question, just whatever they both say, aqueous or solid, go with it. But if they conflict, the rule that's higher up in the list wins out. With this, students, you're now equipped to tackle the homework called Precipitation and Predicting Products. Please attempt that homework for next time in class. And thank you for your really good work today.